Good morning, everyone. We'll get started here in just a couple of minutes. For those of you who just joined, we're going to give a couple of minutes for more attendees to join. Okay, great. It's 9:03. Good morning, everyone. I am Ranjit Deshmukh. I'm an associate professor in the Environmental Studies program and the Bren School of Environmental Science and Management at the University of California, Santa Barbara. I'm excited to welcome you all to the University of California's Climate Action Initiative's Energy Justice Workshop. So let me give you an introduction to the workshop because this is the first panel. We have an exciting set of 4 panels, 2 on each day. So today, our first panel of the day and of the workshop that I'll be moderating is on grid planning for distributed energy resources, or DER adoption and climate resilience. And this is from 9 a.m. to 10:20 a.m. And the title of the second panel for today is Who Bears the Burden? Energy Security and Justice in the Energy Transition. This panel will be from 10:30 a.m. to noon, and it will be moderated by UCSB's 2035 Initiatives Executive Director, Lucas Boyd. Tomorrow's first panel, featuring Commissioner Andrew McAllister, is titled Electrification for Whom? Equity in California's Residential Energy Transition. And that will be moderated by UCSB Professor Grace Wu, and that will start at 9 a.m. So that's tomorrow, Wednesday. And then the last panel, which is again tomorrow, on designing rates and distributed energy for climate resilience, will start tomorrow at 10:30 a.m. And that'll be moderated by UC San Diego Professor Patricia Hidalgo Gonzalez. And the format of all panels will include a 10-minute presentation by each of the panelists, followed by questions from the moderator, and then questions from the audience. So for this audience, please use the Q&A part of this interface. You should be able to also chat with the panelists, but we hope that you can put in your question in the Q&A part of the Zoom. So I hope you get to attend all 4 of our panels. And again, this panel is on grid planning for distributed energy resources, or DER adoption and climate resilience. So with that, let me introduce you to our amazing panelists in this morning's session in the order that they will present. Professor Inês Azevedo is professor in the Department of Energy Science and Engineering at Stanford University, where she studies sustainable energy using a systems approach that combines engineering and technology analysis with economic and decision science approaches. She has published more than 130 peer-reviewed journal papers and has participated as an author to several reports of the U.S. National Academy of Sciences, as well as in the IPCC AR6 report on climate mitigation and the 2024 US National Climate Assessment. Our second panelist, Dr. Ching Tien, serves as a policy advisor to the vice chair at the California Energy Commission, where he works at the intersection of policy, engineering, and innovation to support California's evolving electric grid. With more than 2 decades of experience in the energy sector, his expertise includes distributed energy resource integration, demand forecast and grid planning, reliability analysis, and advancing clean energy technologies from research to real-world deployment. Dr. Tien holds PhD and master's degrees from Virginia Tech and is a licensed professional engineer in mechanical engineering. And our third presentation will be given jointly by our last 3 panelists. So Professor Patricia Hidalgo Gonzalez is an assistant professor and a soon-to-be associate professor in mechanical and aerospace engineering at UC San Diego. She holds a PhD from the Energy and Resources Group at UC Berkeley. Her work focuses on high penetration of renewable energy using optimization, control theory, and data-driven techniques. Currently, she serves as one of the 2 co-leads of the Climate Change and the Energy Sector Appendix for California's 5th Climate Change Assessment. She's also the PI of the multi-campus University of California Climate Action Grant, under which this workshop is being organized. Adam Sedlak is a PhD student at UC San Diego, advised by Professor Hidalgo Gonzalez. He's studying the long-term planning of energy systems and the dynamics of inverter-based grids. And Paul Senatore, he's also a PhD student at UC San Diego and also advised by Professor Hidalgo Gonzalez in inverter-based grid dynamics, game theory, and optimal control. He has a master's degree in applied mathematics and has received opportunity funds from the US government and the Bicentenary Generation Scholarship from the Ministry of Education of Peru. So with that, we have an amazing lineup of panelists. I would love to welcome Professor Inés Azevedo to share her screen and present her slides. Thank you.
Good morning, everyone. Hopefully you can now see my screen. Let me know if not. It is a pleasure to be here today and sharing the opportunity to listen about the results of this important effort and project that was undertaken by the colleagues at University of California. In the few slides I'll present today, I'll mostly set up the stage and mention some of the work that we've been doing in my group on understanding how to better inform US grid planning under both a changing policy context as well as under different types of climate scenarios. Importantly, this is the work of a team, and a team that has been growing over the years here is really all the PhD students and postdoctoral fellows that this research builds upon over the several different years. And I'll go mention specifically some of the recent efforts, namely PIPSA USA, which is a Python-based power system analysis model for the entirety of the continental United States. This was an effort led by PhD candidate Cameron Tiranchi under my group. And it really provides a flexible and open source model that can allow to pursue fast planning scenarios and analysis for the US. We greatly benefited from the PIPSA PSA framework that has been developed by Professor Tom Brown at TU Berlin. And from that, we populated and adjusted the modeling framework with data and policies and considerations that are applicable to the United States. There is really a deep need for models of that sort. Several types of models with different levels of detail exist, and they are there for reasons of understanding the answer to fairly different questions. We do need to understand what are the best investments in both generation, transmission, storage, and how that changes under different scenarios for demand growth, as well as different types of policies. One of the key features is that Pipes USA is open source, so we really want to have different types of users and contributors playing a role moving forward in using this platform. Some key aspects related to it is the fact that it offers a flexible transmission representation. It allows the users to select different nodal resolutions as well as different power flow representations. And so this really helps tailor it to different types of research questions and policy questions that one may have. It also integrates comprehensive data from disparate data sources that are publicly available, including over 60 years of reanalysis climate data that can help us capture how renewable resource availability may change under different types of scenarios, as well as specific generator and storage unit characteristics and policy constraints. So, a little bit about the structure. This type of modeling approach, as it is usual in capacity expansion and operations models, includes detailed data on generators and storage, resource availability, weather, demand, and the specifics of the transmission network. It allows for user configurations, and then it performs a least cost optimization subject to physical power flow, as well as technology and policy constraints. What you get out of this, as traditional again in the nature of these models, we can assess the different portions of system costs, both for transmission and generation, inform decision pathways for technology investments in terms of type of capacity, as well as track the outputs in terms of emissions and potentially on the emissions consequences, both for greenhouse gases and criteria pollutants. The model formulation really looks at minimizing the overall system costs, what we characterize as the system cost, the investment costs for generation and transmission and storage, as well as the operation costs for every single one of these assets. And tying to that, the physics base in terms of including the technology characteristics for generator ramping limits, land use constraints, temporal resource availability, the characterization of the operation of the storage systems and tracking their state of charge, ensuring transmission and power balance across the nodes, as well as including policy relevant constraints such as ensuring that the planning reserve margin is met, regional emissions limits. We include a characterization of renewable portfolio standards across the country, as well as technology capacity targets. Much of this information benefits from the work that has been done over the years across the national labs in the United States, namely the annual READS model that was in place. Populating this model, we included detailed characterization of every single generator asset currently in operation in the United States, as well as a portfolio of potential candidate technologies. We account for different types of exclusion areas on where different types of generation and storage assets can be cited, as well as including different projections for electricity demand across the country. The other level of flexibility is really depending on whether your question requires only a more high-level characterization of transmission versus a more detailed one. We include different Nares-derived N-1 transmission networks that can be used depending on the question at hand. The capacity factors that are including for wind and solar relying on ERA 5 and Go Deep analysis right now. This becomes important to understand how changes in the output of renewable technologies across the nation may impact the optimal decision criteria for investments across different types of assets, as well as transmission expansion. This is work that has been underway by Asia Zhang, a master's student also at Stanford, and for the offshore wind capacity factors by Dr. Niels Angliviel de la Baumel, who did his PhD also at Stanford in civil and environmental engineering under my group. So I'll showcase just a couple of outputs that one can have when addressing these sorts of models. And in this case, those are results across the continental United States. What you see over here is both the share of supply of electricity in 2035 for the top panel and 2050 in the lower panel by technology type. We're seeing this for different scenarios. The first one being a current policy scenarios. By current policy scenarios, we are really representing the current status quo, meaning post-OBA policy being enacted, while at the same time continue to represent the state level policies such as RPSs or other climate goals. The second panel, the 2035 or 2050 RTC, represents the same case as before, but now assuming that the renewable tax credits that were envisioned under IRA were still into play. The third column represents OBA policy world, but assuming that a zero emissions goal would be established for 2050, but without the renewable tax credits being in place. And finally, the last column represents a scenario where we have both renewable tax credits as they were envisioned under the IRA, as well as zero emission scenarios. Although not shown in this figure, the costs associated with these systems would be different. One of the things that we observe is that having a little bit of transmission expansion, which is shown on the horizontal axis, could really go a long way in terms of reducing some of this system total costs. But the other thing that we observe is really that the policy drives a lot in what pertains to the type of generation that would see in the near and even more so in the somehow slightly more distant future. In all cases, the role of onshore wind is quite important, but having renewable tax credits, for example, does magnify the presence of wind even more so if we allow for transmission expansion that can allow the United States to use the resources of wind in the Midwest and connecting them to the other areas in the country. Now, more related to what we're discussing here today is the consideration of how are those different types of investments shaped by changes in climates. We started to grapple with this problem, and these are preliminary results and work, but by thinking how these different investments change when we account for changes in capacity factors for wind and solar under different RCPs. And so this is work from Asia Zhang and jointly in coordination with Dr. Edgar Vigues. We captured the Go Deep data set, once again benefiting from the incredible work from the National Labs ecosystem from PNNL that has put together the Go Deep platform. What are we observing across the continental US? We observe that as we look at different RCP scenarios, we observe that the capacity factors, both for onshore wind and solar, change over time. More striking is the situation for solar, where we see that over time there is a decrease in the capacity factors when compared to 2012 reference case scenario. And that difference also increases as we go into RCP scenarios that are inducing larger climate change. We're still looking at how this differs from region to region across the country and for different sites and the underlying reasons why. But this is one of the first sort of snapshots at this issue. Now, even more to point before we move into the next session, what does this mean for WEC? Here we showed the results also again under different RCP scenarios of the types of optimal investments and electricity generation across different types of technologies. One of the things that we observe is that across different RCPs, there are some changes in the types of technologies that one would select. But even by 2050, which this figure pertains to, the change is not too dramatic. So the results are fairly similar. We also observed that just including the different RCP scenarios also has some impacts in the total annualized system cost for generation, transmission, and storage, with the cost under all RCPs being higher than what we see under the historical one for WEC. Bear in mind that in the results that I'm presenting here, not only they are preliminary, but we're only accounting for the effect on capacity factors. We're not yet including other effects, such as the fact that under different types of RCP scenarios, those would have implications also for the overall levels of electricity demand for cooling, for example. So those are not taken into account just yet. So with that, and whereas this work provides an interesting national picture and as well as for the WEC, much more work is needed, namely in terms of a much better characterization of the role of DER between this entire context. And that is why I am so happy that we have our colleagues next for the continuation of this panel, detailing how they tackle this challenging question specifically for California. Thank you so much.
Thank you so much, Professor Azevedo. That was an excellent presentation, especially incorporating climate change impacts in energy systems planning, which is a pretty challenging task that many researchers are grappling with. So next, I would like to invite Dr. Ching Tien from the California Energy Commission to make his presentation on distributed energy resources.
Can you see my screen?
Yes.
Okay, great. Good morning, everyone. It is a pleasure to be here today. I'm an advisor to Washington, that is a California Energy Commission. Wash is not available today, and he has a conflict, and he asked me to speak on his behalf. For this presentation, I want to touch on why distributed energy resource and demand flex are important to California's clean energy transition, and also how they intersect with broader strategy, planning, and reliability needs. California is targeting economy-wide decarbonization by 2045. So what does this mean? This means widespread electrification. So we have goals set for 5 million zero-emission vehicles by 2030, 100% all in-state sales of zero-emission passenger cars and trucks by 2035. We also are deploying 6 million electric heat pumps by 2030. So as you can see, electrification is really at the heart of our decarbonization strategies for California. As we are making progress toward electrification, California's electricity demand is expected to grow significantly. The recent California Energy Commission's demand forecast shows that the summer peak demand in CAISO territory is expected to grow by 20 gigawatt on top of the 46 gigawatt we see today. So this growth is mainly driven by electrification, as you can see, in the graph on the right side. This includes like 45,000 megawatt for buildings and 8,200 megawatt for transportation. On top of that, there's a 4,700 megawatt for rapid expansion of data centers to support AI and cloud computing. Our recent SB100 study shows California will need to build 10 gigawatt of clean generation resource every year for the next 20 years to meet our climate goal and to meet our load goals. This also required major infrastructure investment. Not several years ago, California CPUC Public Advocate Office and estimated that we will need $26 billion in distribution upgrades by 2030. This includes the major investment for 3 investor-owned utilities. This is where I think distributed energy resource and demand flex can really help by shifting when and how electricity is used to reduce the stress on grid and defer costly upgrades and investment. I also want to touch a little bit on the book grade side. Back in 2016, which is about 10 years ago, CAISO released that fact sheet to illustrate the potential operation challenges due to high penetration of renewables, known as that curve. It is predict a steep 3-hour net load ramp up to 13,000 megawatt by 2020, as shown in the left figure. Fast forward to 2023, those projections didn't just come true, and they have surpassed, as shown in the right figure. And CAISO set a record of nearly 17,000 megawatt net load ramp over just 3 hours. This really underscored the importance of flexible resource for renewable central grid and fast ramping generations, battery storage, demand response are all critical to help balance the system in real time. As we all know, the electricity system is all about balancing supply and demand. And traditionally, we focused on adjusting supply using fossil generators to meet variable demand. As we are moving toward the renewable central grid, it is really important for us to focus on the other side of the equation and demand. With technologies like smart EV charging and smart appliances, battery storage, we now have tools to use electricity when it's clean and cheap, and shift usage when the grid is under stress. It is a time to plan for demand flex and DERs with the same rigor as we do for generation. So this means integrated into our planning models, reliability assessment, real-time operation, and market. So the grid of the future isn't just powered by clean energy resource. It can also be balanced by smart and responsive demand. A major milestone came in 2023 when CEC, working with CPUC, CAISO, we set a statewide goal to meet 7 gigawatt of load shift by 2030. We organized distributed energy resource and demand flex resource into 3 main categories. The first is the load modifying resource, and this include time of use rate, dynamic pricing, and automation. So these tools help shape demand on a regular basis. They play a foundational role and have significant long-term impact on system planning and distribution planning. And smart devices can help unlock the full potential of those load modifying devices by automating how and when load is shaped in response to grid signal. At the CEC, we're also developing standards for these smart appliances to make them grid ready. The second category is about resource planning and procurement program. This include market integrated programs which can be part of the resource adequacy. And the third category is about incremental emergency programs, such as demand side grid support program, which is designed to respond to emergency conditions, offering additional headrooms when the grid is under the most stress. Here, I also want to talk a little bit about the last two categories. The last two categories are about demand response. You can think load modifying resource as like the cruise control of your car. So they're programmed in advance to manage the speed. It runs smoothly and automatically. So the demand response is more like your brake pedal. So it is something like you can rely on when it comes to emergency situations. Our goal is to unlock 7 gigawatt hour flexible load by 2030. As of today, we are about halfway there. When it comes to distributed energy resource, you probably heard a lot, the value stacking. That means the same flexible load can provide values to customers, local distribution systems, to the book grid. But today, those needs are still too often separated by different rules, programs, different signals, and different pathways. As we are going forward, and it is really important to develop a more coordinate and demand flex DER framework. What does this mean? This means interoperable market pathways that help integrate the DER resource from book grid system to the distribution system, share the data infrastructure, a more automated and location-aware flexibility, and a statewide roadmap that can align planning, operation, and performance measure. At the CEC, we see our role to help make DER and demand flex easy to scale statewide. For planning, the key is to bake DERs and demand flex into our demand forecast. And this is why our forecast include load modifiers for efficiency, behind-the-meter batteries, and EV charging. Those inputs also flows into integrated resource planning, transmission planning, local reliability, and distribution planning. We also work on standards and market enabling tool like load management standards, MIDAS, and standards for smart appliances. On program and funding, CEC has programs to move research ideas into pilots, demonstration, and commercialization. So this include EPIC and clean transportation programs, and important partnership like CalFlex Hub, LW Flex Hub. Lastly, I want to thank you for your attention, and it is a pleasure to be here and share our work at the CEC and also be part of this important conversation. Back to you.
Thank you, Dr. Thien. So next, I will invite Dr. Hidalgo Gonzalez, and our two PhD students, Adam Sedlak and Paul Senatore, to make their presentation. Thank you.
All right. Oops. Sorry about the technical hiccups. And thank you so much, Ranjit. And yes, very excited to be here. My name is Patricia Gonzalez, an assistant professor at UC San Diego, and I'll be presenting alongside my two PhD students, Paul Senatore and Adam Sedlak. This is work that comes from a larger project that I'll briefly introduce to provide context to our work. The work is titled Designing California's Clean and Climate Resilient Electricity Grid for Vulnerable Communities, and it's been a collaboration between UC San Diego, UC Santa Barbara, UC Berkeley, and we have been supported by NREL at the time, Berkeley Lab, and Grid Lab. And our work has been split in 4 different thrusts or themes. The first one, where we look at a statewide survey run by UC Santa Barbara, looking at the propensity of adoption of electrifying end uses as well as DERs. The second one looks at microgrid sizing and deployment from a techno-economic perspective as well as a resiliency perspective. And the fourth one looks at tariff design from an equity perspective. These 3 thrusts, you'll hear about some of our work in the panels tomorrow, so definitely tune in if you're interested. And today we'll be talking about some of the work from the third thrust, which looks at capacity expansion modeling when it's mindful of climate change as well as survey-informed loads. And we have been very fortunate to have the support of our technical advisory board as well as our community advisory board. And this is a quick screenshot of our current and past team members, which without them we couldn't have achieved all that we've done over 2.5 years. And it's been really exciting and rewarding to get to collaborate with all these colleagues. And we definitely thank the University of California, the Office of the President, for all the funding and support provided. And with that, in the work that we'll present today, we'll highlight 3 main themes of this manuscript. The first one is that increasing deployment of DERs and residential electrification can result in 33% reduction of investment costs in utility scale generators. If transmission expansion were to be restricted, California should ultimately deploy between 4 to 5 times more residential PV. And last, least cost planning can serve as a tool to achieve equal levels of first household residential PV capacity in disadvantaged and non-disadvantaged communities. So now let's quickly talk about the setup that we have. So we're using the statewide survey that achieved more than 7,000 responses from Californian households, and this was administered by UC Santa Barbara. And that survey informs the load scenarios that we have. In terms of the capacity expansion that we do, we focus in 2035, and we model almost 9,000 nodes in the grid, and this is building upon the prior work from Lina Roll's group at Wisconsin-Madison, which we're very grateful for. And on top of that, we layered different 4 climate projections that affect the loads and the supply. And for the modeling of the loads at the substation level, it was a very fine, detailed work, also led by UC Santa Barbara, where they looked at the feeder information across the different utilities, looking at the different buildings that were connected to each feeders, and then aggregating these loads all the way to the substation level for each of the substations that we're modeling. All this informed by the survey. And now I'll quickly give you an overview of what's the setup of optimization and the scenarios that we're running so you can interpret well the results. So we have 3 different scenarios for loads, one where we don't provide any incentives for electrification, one where we provide low incentives to electrify, and one where we provide high incentives to electrify. And in terms of the capacity expansion, the utility scale generators are optimized to achieve least cost, but we have 3 different ways to optimize the deployment of DERs. The first one that we call the freely optimized is the classical capacity expansion model that does least cost optimization without considering the survey. In the second one that we call at least survey, what is happening at each substation is that we're forcing a constraint that the DERs deployed has to be the same as the survey or more than what the survey is projecting. And in the third type of optimization that we call the equal to survey is where we force at each substation to deploy exactly the amount of DERs that the survey says we should do. And last, we do sensitivity on transmission expansion, where 100% represents freely optimized least cost solution for transmission expansion. And then we do a set of separate independent runs where we go restricting how much transmission can be expanded for 2035, all the way to 0%, which means no transmission expansion is allowed. And with that, we'll dive into the highlights. Thank you, Paul.
Yeah. Okay, thank you, Patricia. So highlight number one, it's about the benefits when we incorporate social propensity of DR adoption into least cost planning. So first, we highlight that when we are deploying DRs driven by social propensity, we have a reduction of 33% in utility investment costs. So we can see this in these two panels that we are showing. We have in the left-hand side that really optimize simulations, and we have in the right-hand side equal to survey. For each of the panels, we have 3 levels of residential electrification incentive going from none to high. So what we can see in the right-hand side, when we have the equal to survey, when we are going from none to high, we can see that the portions associated to utility scale investment costs, they are reducing. So this is about $3.1 billion. And second, we can see that 58% reduction in deployed transmission capacity in the full system. Next, if we can see, we also quantify the transmission losses and curtail energy when we deploy DRs given by the social propensity. So we see that 20% reduction in transmission losses and also 34% reduction in curtail energy. And next, we also quantify the variation of locational marginal prices in the system. So you can see in the left-hand side a panel in which we have in the x-axis the different hours of the day, and we can see in the y-axis the locational marginal price in dollars per megawatt hour. So we can see that when we are going from none to high, it means that we are increasing the electrification incentive. We are introducing more DRs. We can see that the distribution of LMPs, they get smaller. So if we quantify this is a 56% reduction in the 95th percentile of electricity prices across the system. So the high number two is about what if the transmission expansion in California is restricted. So first, we quantify the deployment, the variations in deployment for residential PV and batteries when we are varying the transmission deployment in the system. As you can see in the x-axis going from 0 to 100, and also we have CP, that means copper plate. So first is the first point that we have to want to highlight is that when we decrease the transmission deployment, it means that we are going from the right to the left-hand side. So we can see that the residential PV increases 4 to 5 times in very low transmission expansion, and this corresponds to 5 to 6 times of today's residential PV capacity. And also, one important point is that we wouldn't be able to capture these deployments in residential PV and batteries if we would have used copper plate or sonar models. As you can see in these two panels, when we are in CP, copper plate, we get extremely low levels of DRs, residential PV and batteries. So we conclude that when we use copper plate models, we fail to capture deployment of DRs. That's why in this work, if you see in the right-hand side panel, we can see that the different levels of deployments of residential PV across the substations or nodes that we consider in this work. And finally, since we are using a high geographical model, we are able to quantify the variation of locational marginal prices across the system. And as you can see, as the transmission deployment is decreasing, going from the right to the left, we can see that LMPs, the electricity prices, are increasing in distribution. Finally, we have the utility PV deployment and also utility batteries across the system. As you can see, as we decrease the deployed transmission going from 100 to 0%, we can see more deployment of PV and batteries in Southern California. Now, Adam will speak about highlight number 3.
Thank you, Paul. So the third finding from this work has looked at where residential investments in PV are being deployed across the state. And because we're using a very high resolution node model, we can map each node's investments to census tracts. So what I'm showing here on the left is a figure with the PV investment across the state, where each dot size represents how much residential PV was added at that node. And the color is used to distinguish between orange, where a community is classified as non-disadvantaged by the state, and purple classified as disadvantaged by the state, according to SB 535. And as you can see, there's a large scale PV investments in most of the most populated areas of the state when we use when we follow the electrification that our survey projected. We compare this to the case where we allow our model to build above what we project the social propensities of PV deployment to be in 2035 and find very similar results, but a few notable differences where additional PV was added in parts of LA, the San Joaquin Valley, and Sacramento. We contrast this with the case where we plan from a least cost perspective without considering what residential consumers will do on their end, and only what is necessary from a system perspective. And as you can see, significantly less residential PV is needed to be deployed in these case studies, but there are potentially more equal levels of deployment between different community types, disadvantage and non-disadvantage. So this led us to want to quantify this more precisely. So what I'm showing here is the maximum amount of PV that we could deploy in each community type in kilowatts per household. So I want to draw your attention to the green box, which is the first plot I showed you in the previous slide of what our survey is projecting. You can see between 1 to 2.5 kilowatts per household, and comparing this with the freely optimized case, which is the least cost system planning perspective, which ranges between about 0.5 to 1.5 kilowatts per household. This is contrasted with the non-energy disadvantaged communities. And what I really want to highlight in this plot is the difference between the green and red boxes. So the fact that this green box is a little bit higher in non-disadvantaged communities is telling us that on a per household, per capita basis, non-disadvantaged communities are getting slightly more investments in residential PV when we follow social propensities. Whereas when we follow the least cost planning perspective, the two investments at a per capita basis appear more similar. So we quantify this more precisely in our final plot where we take the difference of these two. And indeed, in fact, we can confirm that there's not a significant difference in the deployment between community types when we follow least cost planning, which is particularly striking because our model didn't explicitly consider whether a given community was energy disadvantaged or not. So this is telling us that least cost planning can be an effective tool to plan and deploy PV in a way without exacerbating existing disparities. So to recap what we've shown you today from our paper, increasing levels of distributed energy resources and electrification incentives can result in a reduction in utility scale investment costs. If transmission is restricted, California may need to deploy 4 to 5 times more residential solar PV. And finally, least cost planning can serve as a tool to deploy PV in equal manners between disadvantaged communities and not disadvantaged communities.
Thanks, Adam. And with that, we'd like to thank you for being here. We look forward to the panel session. And you're very welcome to use the code and the data that has been developed under this project. These two have been developed under the project, and Katz is from the team at Wisconsin where we built upon. Thank you so much.
Well, thank you, Patricia, Adam, and Paul. I really appreciate it. So maybe all panelists are on the screen now. Dr. Thien, maybe if you can turn on your video on. I have 4 broader questions that will start our discussion. I'll direct, the first couple of questions to particular folks here, and then we will go to the Q&A. But there are some specific questions in the Q&A on, some results of studies. So if anyone wants to, type your answers there, you're also welcome to do that. Okay, so my first question, so the questions are as follows, right? So I'm going to talk about or ask about climate change impacts first, and then we'll move to DER in terms of modeling and planning, and then we'll move to actual implementation. So my first question is directed at Professor Azevedo. So, and then I want everyone else to also chime in for each of these questions. So what advances do we need to make to incorporate the effects of climate change in our models? And then what solutions do you see in terms of investments and operations that would mitigate those effects?
Thank you so much for the question, Ranjit. I think the needs to incorporate climate effects go across different levels. First and foremost, having a good characterization and a granular one of potential climate scenarios in terms of the fundamental physical and weather-related data, really, in terms of solar irradiance, wind speeds. So having that ground source sort of scenarios to play with would be really important. One of the things that we've been observing is that sometimes from those initial sets of data to capacity factors, you're embedding a lot of technology assumptions, right, in terms of the specific type of Vestas turbine that is considered and whatnot. So having that very transparent path from types of solar panels to the physical quantities and how that is evolving according with the new technologies is an important step one. The second one that seems a key priority related to climate is that I think we still know little about the sensitivity of electricity demand to temperature. We have some models relating that through heating degree days, cooling degree days, some very simple relationships. But all of that may be changing and changing under extremes and as a function of the price signals that are provided and as part of the affordability. So I would say that that's dimension two. And dimension three is on the portions of the system that still rely on thermal power plants. What will be the effects of those changes on cooling needs for the power plants themselves? So that entire system would need to be a little bit more captured. And if you permit me, I'll add one more layer on this, which doesn't relate directly to climate, but I think it's front and center on everyone's minds, which is what will demand for electricity look like in California and across several places in the nation as we think not only about large electrification of some end users, with or absent climate policy, but even more so as we have these uncertain large loads from data centers and AI, which likely will materialize to a very large extent, but still with an enormous uncertainty on what that is going to look like in the next 2-3 years. Table on top of that, the cooling needs of data centers under climate change scenarios. I think that will be another interesting area to explore.
Great. Patricia or Ching, Dr. Tien, would you like to add to this?
I think Ganesh covered it really well. I would say it would be important for the state, as you know, the state has been investing so much money into these data sets, climate-informed data, and so forth, that now we start moving more into the direction of considering, as in Inesh work, like a myriad of different futures and looking at how can we be resilient to those. And yeah, in our work, I didn't mention it, but it's also stochastic optimization. And I would suggest that maybe the state can consider going into that direction if it makes sense for the IRP, for example.
If I may add one more thing on the second part of your question, Ranjit, on trying to think about what different types of changes and investments may be needed to mitigate those effects. So yes, layer number one would be to understand the dimensions and the importance of those and whether they're indeed very large or not. but the consideration in terms of solutions to mitigate some of those effects really goes into trying to understand a little bit better how can we move from a perspective of reliability to one of resilience and adaptation to the conditions too. So starting to having a better grasp on both the impacts and what sort of investments can be done at the household level, at the transmission level, at the wildfire prevention level, that would really pay off in terms of reducing our exposure to those risks. And that becomes harder and harder in terms from a modeling perspective, but I think that it would be incredibly important for the state to start emphasizing more that in both the modeling and in the decision processes and investments pursued.
That's great. Thank you. And I know, Patricia, you have some research on looking at public safety power shutoff events and how could potentially DERs can play a role in sort of mitigating that. Which sort of brings me to my second question, because one of the solutions, especially as we saw in Dr. Thien's presentation was, and maybe I'll direct this question first to Dr. Thien, is if you can summarize again, what role do you see for DERs to play in making California's grid more resilient to the effects of climate change? But then following that, maybe you can extend on how are DERs currently planned in the IRP processes and could it be improved? And then when you can pass the baton to Patricia and Inej, maybe you all can look at, say a little bit more about modeling advances needed to capture DER uncertainty behavior, as well as the spatial granularity in those planning tools.
Yeah, thanks for the question. I think, DER has a lot of value, bill savings to customers, the resilience, if it's a microgrid, I think someone on the panel mentioned, provides that additional backup, when during, the great, public shut-off. There has been a lot of research done, on the microgrid side, how that might be, benefit communities, critical facilities. I want to touch a little bit on the, maybe take it one step back. Speaking of the DERs, because we do see a lot of value, and especially, I think the previous, the panelists mentioned how to help planning and also, mitigate some of the investment. But what I really want to mention is since we are talking about the extreme events, the wildfire, I just laid out those three different buckets, right? So, I want to touch a little bit about our planning process because, we in California, we have, the PRMs, we follow a traditional planning standards, just taking into consideration of, if there's any power plant outage, if there's any forecasting uncertainty. But as we, because of the recent years, we see more and more wildfires, extreme events. And we felt like that, planning, traditional planning standard no longer work very well. So that's the reason why we introduced another layer to that. So that's what we call, incremental emergency programs. Those basically are the resources we can use to help, when it comes to we have a long extreme heat waves and with wildfire risk, and basically to help mitigate those risks. One of the lessons learned, back in 2022, there was a historical event. The CAISO peak was around 52 gigawatt, which is 7-8 gigawatt, more than what we normally expect. So how you can really address that risk is a big question to us. So I remember, at the time we have to contact the battery owners, ask them to help us to support the grid. So that's the reason why, at the 2023, the state come up with SRR, Strategic Reliability Reserve. We developed the DSGS program. Basically, we are looking into existing DER resources, how we can leverage those to support the grid and when we really need it. So in a nutshell, I felt like DER can play a really important role in terms of like supporting our grid operation. The second question is more about the planning. How demand flex DER is including the modeling process. At the CEC, we are mainly focused on the system level planning. So we are going from top-down approach. So when it comes to DER demand flex, I felt like some of those has been baked into our forecast. For example, the time of use rate, I felt like those has been captured. And also, CEC's demand forecast also fits into, the planning product downstream. For example, the RA procurement, transmission planning. So all of those information I felt like has been on the TOU side. I felt like it's being captured, but there's still some gaps. For example, as we are moving toward dynamic pricing, how are we going to consider that in our planning forecast? There's another element because I felt like in my point of view, DER demand flex, they are more locational wise, based. How to reflect that at the same system level that requires more like a bottom-up approach. So, but anyway, that's for me.
So there's a lot of uncertainty. Patricia and Anish, do you want to add in terms of like modeling advances that are needed to capture this DER uncertainty behavior or spatial granularity, speaking to some of your research?
Right, I'll jump in and then Anish. Okay. Yeah, I think there's a lot of open questions that we need to tackle collectively, which is why collaborations, across universities, labs, government, I think are so, and industry, of course, are so important. And in this work, as we showed, we did like a first attempt to try to bridge some of that gap. And I mean, it was a lot of fun. And we think that we have been able to provide new information that wasn't there before from a geographical resolution perspective by, modeling substations across the state, doing capacity expansion, considering propensity of adoption from people. And I would say, yeah, Ranjit led with the UCSB team the effort on modeling the loads and modeling the DR propensity of adoption based on a set of incentives. And that was a lot of work. So I think something that could help us keep moving in that direction to tap into this DSO, TSO coordination would be to get more access to data. For example, loads from at the substation level, from the electric utilities, from the co-ops. That would be fantastic because our team spends so much time creating those data sets. So if we can have the actual ones and, academics, national labs and so forth, that would definitely help us bring more to this discussion on what are possible solutions, what are drawbacks and risks of also relying on consumers, right? Prosumers, as that's the other piece that we haven't mentioned as much, but there are prosumers, are people, there's human behavior involved in the operation and usage of appliances and DERs. So that brings a risk. And of course, the state needs to be very mindful of how much can we rely on that type of response? How can we cluster across the state to make sure that we can get certain statistical response from a given group of DRs or of prosumers? But it's really non-trivial, right? Because we also have the grid across this. We cannot just look at people across the state and classify them based on behavior. We have the constraint that power needs to flow through the grid. And that's a really challenging piece because, yeah, now we're moving into these nodal models. We have, the 10,000 transmission lines, and that's great, but we don't have the distribution models, right? That's the other bottleneck. Like if we want power from the people, we need to have that full pipeline to understand end to end what are the possibilities. And that's when it becomes fully untractable from a computation perspective. So I think in that end, a lot of decomposition techniques could have a role in that space. looking at GPU usage, which in general in capacity expansion we don't tend to use, so how to parallelize, decompose, parallelize to get solutions. So drawing a lot more from our computer science colleagues, I think in general that I've been an advocate for energy systems to be closer to those type of disciplines so we can tackle more realistic questions with much more robust data sets, for instance. And yeah, I'll stop there and I'll let Ines chime in as well.
Yeah, I'll just also add in that regard and in terms of adjacent fields and attention that understanding consumer adoption and behavior is the other sort of big bucket, and I think the starting with the survey data is definitely a wonderful step. And we know that then the adoption patterns will react to the different expectation of incentives, but that even under perfect information, people may depart to what we would assume would be the optimal choice. And not only that, even if all the incentives are in place, you may get some surprises. So some of the work more on the vehicle charging patterns that with my colleague Ram Rajagopal and Siobhan Powell, we performed a couple 2 or 3 years ago, really learned a lot by just understanding how different types of folks would charge their vehicles across California, and identifying the sort of misalignment between what would be optimal from an environmental point of view versus just the charging when you get home, namely in the context of California, where you could take advantage of the solar energy in the middle of the day, but perhaps not having the charging capacity to do so at work. So I think all of this to say that a claim for having as much data available to researchers in the form of consumption and load profiles and charging would really equip us to be able to pursue better simulations and having that more broadly available to run different types of scenarios. And relatedly, I think there is a lack of modeling across the different changes in the NEM and other DR-related policies and how they will be evolving in the future. Some work on that from the respective teams, but still a little bit more to do, taking into account on how those are going to likely to evolve in the next 2 to 5 years.
That's great. Thank you. My last question, and I'm going to combine it with one of the questions here in the chat is, so what do you see as the biggest institutional or regulatory bottlenecks that might be slowing DER adoption and integration? Because we have established, DERs can play a big role, right, in providing resiliency, perhaps like reducing bills, etc. But what are the biggest hurdles? And then I'm going to combine that with the fact that who benefits from these DERs, like especially if we want more equitable adoption across different communities within California, how do we ensure that that adoption is more equitable, the incentives are more spread out, especially with like rural communities or disadvantaged communities, tribal nations that are more remote? How can they benefit from these programs? So maybe we'll start with Dr. Thien first, given that he represents the CEC.
I can touch a little bit because I felt like the main challenge we need to tackle is how to create a framework that can demonstrate a great benefit and also equitable approach. What I mean by that is there has been a lot of discussion talk about the benefit of the DERs. At the same time, we also heard a lot of like different perspective. There are I feel like what we really need to demonstrate is how DER can help reduce system cost. to answer this question, we really need to know where are those opportunities are located, and to quantify that. And then there's also some discussion about the cost shift, because I remember there was a report a few years ago talking about solar, the cost shift, how does that cause a problem to the ratepayers. I think at the end of the day is we really need to demonstrate the value in a good way, and also on the and also we need to make sure when we deploy DER projects, and the value is not only the benefit only is not only goes to a certain group of the people, because we see there's a discussion about the rich people can afford battery storage, how the low income and dark communities can also benefit from that. There has been a lot of on the CEC side, we have programs on the specific requirement to make sure we have inclusion of those communities, especially when it comes to the storage project and solar project, just to make sure those benefits goes directly to those communities.
Patricia and Inesh, would you like to chime in, especially because the results that Patricia, Paul, and Adam shared in the freely optimized scenario, you saw much more equitable deployment of DERs, but then the question is, how do you incentivize those in terms of adoption? Like, how do you view that?
Yes, I think that's a challenging question to solve. I think, or our take has been incentives, as Ching was mentioning. So targeting those incentives so communities can have access to this otherwise cost prohibitive technologies from a capital cost perspective. So then, as you were mentioning, Ranjit, in the freely optimized case, we still see the RC deployed, which is something that we haven't seen in zonal capacity expansion modeling. So that was really groundbreaking from this work. So I think we are able to capture the value for the state. Now it's a matter of, can we show to the state that there's savings in doing so, and can those savings perhaps be interpreted as incentives to then subsidize for these communities this type of deployment? That would be our next question. And then even beyond that, from just like a political decision, how are we using our taxes? Is it worthwhile spending more money from that angle into deploying, resiliency solutions as DERs? So those are more questions that, in my view, are less of engineering and more of the political side of how do we want to spend our money? How do we value resiliency, access to clean electricity? And that's a really hard topic, right? There's no black and white answer, but it's important. And that's why I've been so happy to be in California for my research career, because the state's truly thinking about those questions deeply, how to incorporate that in their processes, in their planning, in their decision making. So it's not just about money and energy, but it's about the people and how do we guarantee that everyone enjoys this transition.
That's great. Thank you. I'm going to combine a few of the questions in the Q&A. So there's some concern that adoption of DERs, like how that would affect electricity rates for, let's say, the rest of the non-adopters. But then also on the technical side, do you see issues with system stability, or I'm guessing more inertial response, etc. So there's the technical part of it on how a deeper penetration of DERs would affect the whole system, but also on the regulatory and rate side, and how would that affect sort of rate design and perhaps inequity in who bears the burden of supporting the grid infrastructure. It's not directed at any particular person, but feel free to.
I can jump in. Or go ahead, Ching.
Yeah, I can comment on the rate side because CEC, we don't do rates, but I can talk a little bit about the DER impact to the grid. I think there has been a lot of discussion like on inverter-based resource, how those might impact the operation. And I feel like that there has been some work on grid forming inverters. I think that's to help address those issues. That's what I know about how to. Back to you, Patricia. Sorry.
No, thank you. I think you're right on point. I understand the concern of people about low inertia systems. However, power electronics and DRs who are interfaced with an inverter respond a lot quicker than traditional generators like thermal plants. So if we are able to design a scheme that controls DRs in clusters, then we have the potential to operate the grid in a more efficient way. It's just a matter of that we need to do it. We need to be proactive about it. We shouldn't just let things happen and see how this evolves. But we need to be very proactive on what are the standards and regulations and requirements for the response of these inverters to make sure that they are doing what they need in transient, in the short term that we're looking at. And on that end, in my group, we have work in that space. Happy to talk about it in a different setting, but there's a lot of opportunity. So we see it more as an opportunity rather than as a problem.
I'll just add to that in thinking that the design of the DR incentives themselves will, of course, have key implications, and unfortunately, we're not starting, or fortunately, we're not starting with a blank slate, and there are precedents on how they were designed, where they were already winners and losers, and so it's incredibly tricky right now in terms of designing something moving forward where adopters are not anchoring on what they've seen previously in terms of the high rewards of being PV owners and participating in DER versus what it looks like moving into the future. With that said, I think there are opportunities and mechanisms to create win-win solutions moving forward if those incentives are really well designed and benefit the system overall in terms of lowering the system costs too. And I think more on the good news, we are seeing both the cost of solar PV and storage inverters coming down sufficiently to enable that to be a reality now.
Yeah, I think the technological changes that we're seeing are definitely going to, accelerate this transition. I know we have just a couple of minutes left, and I feel like just one last thing, and maybe we can just be really brief about it. The big elephant in the room is data centers and data center growth. It's like a chicken and egg thing too, how quickly data centers are going to grow and potentially affect rates or just congestion in the system. How do you see DERs play a role in sort of mitigating that? Are people going to adopt more in response to rates, or is it just like responding to NEM 3.0? Like how do you view that sort of churn that is happening in the power sector?
So maybe I'll chime in just saying that this is one case where we probably need to be very comfortable departing from optimality in a solution, right? I think probably in the next 2 to 3 years, we really just need to have the ability to build and scale these data centers in response to AI. And it may be the case that flexibility is not going to be embedded or front and center right now. And I think that's fine, right? We may not be able to sort everything at the same time, but definitely starting to build collaborations and knowledge with the hyperscalers to understand where is the potential for flexibility and what sorts of signals could be provided in the future so that they would indeed want to scale up and provide services in that regard. If we end up in a best of all worlds, and that is including per design right now, great. But my sense is that the push for growth is so strong and so immediate that we just need to solve that problem first. And perhaps worry less about situations of lock-in in the way that we do for long-term large infrastructure planning, because there will be some flexibility down the line. So I think it's a different type of problem. So I'm reasonably optimistic on that one. Yeah.
That's great. I think this is a great way to end the panel here at 10:20. Please join me in thanking our panelists for today. It has been a great, exciting conversation. So I really appreciate you for taking the time. Our next panel for today is who bears the burden? Energy security, energy insecurity and justice in the energy transition. And this panel will start at 10:30 in 10 minutes and will be moderated by UCSB's 2035 Initiatives Executive Director, Lucas Boyd. Please stay on. We have a great set of panelists. So thank you once again. The link is the same, and we will see you shortly. Thanks so much.
Thank you all.
All right. Hello, everybody. I think we're going to go ahead and get started with our second panel of today. My name is Lucas Boyd, and like Ranjit mentioned, I'm the Executive Director at UCSB's 2035 Initiative, which is our think and do tank here focused on addressing the climate crisis in the near term. And I will be moderating this second panel titled Who Bears the Burden? Energy Insecurity and Justice in the Energy Transition. For those who just might be joining us, maybe you missed the first panel, this workshop brings together researchers, practitioners, and policymakers really working on these big questions of energy equity and justice. And this is our final panel of today, but we have another two panels tomorrow, same time, same place. So tune in then as well. But let's get to it. I'm thrilled to be moderating this particular session because I think it really gets to the heart of the work. Because in my world of climate policy, this idea of energy transition is often framed as this unambiguous good, right? Cleaner air, less pollution, fast cars, better technologies, everybody's happy, healthy, prosperous, solar panels everywhere. It's a beautiful vision. And I think an energy transition can be all of those things, and we should strive to make it all of those things. But we also need to question that sometimes rose-colored outlook on what energy transition is. And I think these three panelists are going to ask some pointed questions that really get to the heart of that. How do low-income communities and communities of color actually experience the energy system? And as we begin to transition that system, who bears the costs and who is going to benefit? And how do we make sure we're not leaving communities behind? And on from there. We'll dig into all of this over the next hour and a half or so. But let me go ahead and introduce our three esteemed panelists. Dr. Michelle Graff is an assistant professor at the Jimmy and Rosalind Carter School of Public Policy at Georgia Tech. Her work focuses on residential energy use, energy insecurity, and the behavioral and structural factors that shape how households interact with our energy system. Today, Michelle's going to present her research on how people use their thermostats and how that can actually lead to energy insecurity. Sage Kime is a PhD student in urban planning and public policy at UC Irvine. She researches environmental justice, energy transitions, and collaborative governance. And today, she's going to discuss energy and equity justice issues in energy transitions and present an analytical framework to help us understand those. Dr. Sergio Castellanos is an assistant professor at UT Austin, where he leads the RESET Lab, which is a clever acronym that stands for Rapid, Equitable, and Sustainable Energy Transitions, where he analyzes just decarbonization pathways for emerging economies, data-driven sustainable transportation approaches, and equitable local energy transitions. Today, he's going to share his study on the disparate diffusion of rooftop solar in communities, the financial consequences, and why we are seeing those patterns. So here's how this is going to go down. Just like the last session, if you were here for that, each of our panelists will share a brief, roughly 10 minutes or so presentation of their work. Then we will move to a Q&A. I will ask a few questions to kick us off, and then the last part, we will open it up to audience questions. So as we're going throughout the presentations, please drop questions into that Q&A box at the bottom of your Zoom screen, and I'll be looking at those throughout and get to many of them towards the end. And with that, let's get rolling. I will hand it over to our first presenter, Michelle. Take it away.
Thank you so much for that introduction. I'll go ahead and share my screen. Let's see if I can. Actually, before I do that, let me turn it into failure mode. All right, share. And all right, can you guys all see my slides? Hopefully. All right. Well, I'll go ahead and get started. Again, I won't reintroduce myself, but I am Michelle Graff. I'm going to be talking today about some work that focuses on the role of thermostats and human behavior in residences in the United States. This work was largely motivated by the understanding that a safe indoor environment is really vital for residential health across the globe and here in the United States. But in 2020, about 10% of US households actually reported that they were unable to keep their indoor temperatures at a safe or comfortable spot due to energy cost concerns. We also know that heating and cooling our residences accounts for over 50% of energy consumption in the United States. And oh, sorry, I'm getting a message. Can we switch to, yes, let's see. If I switch to this, can you guys still see my slides? Okay, well, holler if you cannot. Perfect. Okay, great. Thanks, Carrie. I appreciate it. And heating and cooling account for over 50% of home energy consumption in the US. But the drivers of this temperature regulation in US residences remains like pretty poorly understood. It's pretty well documented, but it's poorly understood at a national scale. We think that there are two main pathways to understanding thermostat control. The first is technology pathway, like exactly what type of technology thermostats do people have in their homes. Some conclusions that have been made by the literature is that smart thermostats, as compared to potentially manual or no thermostats, reduce energy consumption due to their automation and Wi-Fi connection, which allows them to adjust due to occupancy and external temperatures. But there's other work that also shows that programmable thermostats actually fail to deliver these energy cost savings or reduce energy consumption due to occupant misuse, which leads to our second pathway, which is occupant behavior. So this idea that user engagement might actually be a predictor of thermostat settings rather than the actual technology in people's homes, and it actually may dominate technology effects. So we set off to better understand at a national scale what factors are driving residential thermostat settings in the US with a focus on thermostat type and use behavior. We rely on the Energy Information Administration's Residential Energy Consumption Survey, or the RECS. It's a nationally representative sample, and it was included in the most recent RECS collection were state level identifiers, which allowed us to do some important fixed effects later in our modeling strategy that I'll talk about. Our dependent variable was a continuous measure of indoor thermostat settings ranging from 50 degrees Fahrenheit to 90 degrees Fahrenheit. We have this delineated by season, both winter and summer months, as well as occupancy. So if somebody is home during the day, gone during the day, or in the evening, what are they setting their thermostat settings at? Our explanatory variables are the two pathways that I started to describe earlier, including the thermostat type in a residence's home, as well as thermostat control behavior. So this includes a programmable thermostat, a manual thermostat, a smart thermostat, or no thermostat in the home. And control behavior were things like whether a respondent set their temperature and just left it throughout the day, manually adjusting their thermostat throughout the day, or turning their equipment on and off as necessary, automatically adjusting due to Wi-Fi connection. So these are more the automation settings, or they do not have control over their thermostat settings. The REX allows us to include a rich set of covariates, including respondent level, housing level, and location level identifiers that aim to reduce any omitted variable bias when we're trying to understand the connection between thermostat type and occupant behavior. So we have this rich set of covariates included in our models. We use a survey-weighted linear regression for our primary specification due to the continuous measure of thermostat settings. And we include thermostat type, behavior, and our rich set of covariates as well. So this is a look at our first set of results. These are our winter thermostat settings. So just to orient you, because I know this is a lot of results on a single page, panel A, you're looking at the behavior and thermostat results. Panel B, you're looking at the respondent characteristics. There are three regressions. Black is when people are home during the day. Gray is in the evening, and blue is during the day when folks are gone, not home. There are a couple of main takeaways that I just want to definitely touch on here because the patterns persist between the winter and summer months. You can see that in panel A, those that are setting their temperature and leaving it or manually adjusting it are actually setting their temperatures higher than those who rely on automation or smart thermostats to control their thermostat settings. However, if you look a little bit farther down on panel A, you can see that the type of thermostat people are using doesn't seem to be having a meaningful impact on where they are setting their thermostat in the winter. So in this, we're sort of seeing behavior be a pretty consistent indicator of people's thermostat settings, whereas controlling for thermostat type doesn't seem to be as much of an indicator. I also want to point out on panel B, although income does have a relationship with winter thermostat settings, just take a look at that estimate on Black household respondents and other race that are other than Black, Hispanic, or white respondents. Those households are setting their temperatures up to 2 or 2.5 degrees higher in the winter than white households. That's a pattern that I just want to point out because it's something that is fairly consistent across our results that we were not expecting. This is a look at the summer thermostat settings. Again, the same setup with panel A and panel B and the three regressions. You can see the pattern sort of persists, where folks who are setting their temperature and leaving it, and folks who are manually adjusting it are setting them lower in the summer, and Black respondents are also setting their temperatures up to 1.5 degrees lower than white respondents, whereas thermostat type, that type of technology, really isn't a consistent indicator across occupancy in the summer as well. So we sort of see some consistent patterns of behavior being an indicator pretty consistently of thermostat settings in winter and summer, as well as race. So we wanted to probe this a little bit more. So we asked 2 follow-up questions. What characteristics are actually associated with the thermostat type, and what responded characteristics are associated with those temperature control behaviors? So again, I'm going to open with a big set of results. We use survey-weighted logistic regressions here because our dependent variables are now binary, thermostat type and temperature control behavior. So now we're looking at the odds ratio of the type of thermostat that someone has in their home. Panel A is looking at income characteristics. Panel B is more demographics. 4 regressions. Black is you do not have a thermostat in your home. Gray is a manual thermostat. Blue is programmable. And green is a smart thermostat. Consistent results show that vulnerable populations, lower income, renters, Black households are more likely to not have a thermostat and less likely to have a smart thermostat. This, of course, is pretty consistent with prior literature showing that vulnerable populations have less control over their thermostat setting and less access to energy efficient technologies. Related to temperature control behavior is a similar pattern. So Black is those who set one temperature and leave it. Gray is manually adjusting. Blue is turning on and off. Green is no control, and pink is auto adjusting. You can see across most of the vulnerable populations, income, renters, Black households, they're less likely to be able to automatically adjust, likely because they are less likely to have a smart thermostat as well. We also see some of these income measures being correlated with more likely to have to no control and more likely to set their temperature at one place and leave it throughout the day. A less efficient, energy efficient option, temperature control behavior. So really briefly, taken in totality, we think that these temperature control behaviors seem to have an influence on thermostat settings that we want to probe more. Unexpectedly, we see racial disparities having this impact on thermostat settings, but vulnerable groups in general corroborates previous evidence, have lack of control of thermostats and less control to smart thermostats or technology as well. We think this leads to some policy implications that corroborates, again, other evidence. We really have to tackle these infrastructure gaps, especially with smart thermostats. But one thing that we could add to another policy dimension is if we cannot efficiently and effectively deploy these smart thermostats, can we encourage educational initiatives? So promoting training on efficient thermostat use, regardless of which type of thermostat you have. So considering adjusting your thermostat based on occupancy, day versus night, home versus not home. And this would allow people to engage with thermostats to improve efficiency without really risking comfort. To further probe this, I won't go too deep in this, but our next steps in this work is a 4-wave nationally representative sample of US households because the REX is a cross-section. So we want to see if there's more seasonal variation that we can capture about the impact of occupant behavior on energy consumption patterns and thermostat use. This is actually going to be launched in September 2026. And the goal is to have a nationally representative sample and a pretty substantial oversample of Black households to help us understand these racial disparities. That's all for me today. Thank you so much again for having me, and I'm thrilled to answer questions when we get to the Q&A section. Thank you so much, Dr. Boyd.
Thanks so much, Michelle. With that, I will go ahead and turn it over to our second panelist, which is Sage. Go ahead and share your slides and take it away.
Let me try to share. Okay, how's that? Can you guys see? Okay, perfect. Oh no, I lost it. So sorry. Okay, great. I am hoping everybody can see okay. Hi, everybody. My name is Sage. I'm a PhD student at UC Irvine, and today I'll be talking about equity metrics for low carbon energy transitions. And this is based off of work I did in a previous paper that I've highlighted right here. Okay, so first I kind of just want to start off with this concept of an equitable energy transition. Lucas had talked a little bit about this in his introduction, but when we think about the low carbon energy transition and this kind of shift away from fossil fuels, I think there are some really clear benefits that we like to highlight. So reduced emissions, improved air quality, and improved public health. But those benefits aren't always distributed evenly. And we're already seeing other types of burdens and costs as well. So things like unequal access to energy technologies, persistent energy insecurity, and even economic disruption in regions that depend on fossil fuel industries. And these impacts have disproportionately affected people of color and low-income communities. And this is where this idea of a just transition comes in. So one that prioritizes the health and well-being of these communities, particularly those who have been historically impacted by energy systems. But achieving that really requires more than just intent or ambition. It requires actually evaluating how these impacts are distributed in practice. So this is kind of where metrics come in. So metrics can allow us to establish baseline conditions, identify disparities across populations, and evaluate how policies are performing over time. And they can also play a role in supporting accountability and transparency in decision making. But one of the main challenges and part of what motivated this work is that existing approaches to measuring energy equity are pretty fragmented. So different disciplines and different sectors have used different types of metrics and often focused on different types of equity impacts. So while equity is a common goal and widely discussed, it's often difficult to evaluate in a systematic or consistent way. And without a more consistent approach, it remains difficult to operationalize in practice. So that kind of brings us to our project, which is based on a broad interdisciplinary literature review. We reviewed over 400 articles and reports and identified equity relevant metrics from about 130 studies across disciplines, so things like public health, energy systems, and economics. And importantly, a lot of the times these metrics didn't actually reference the word equity. They were more so just referenced in terms of like explaining the impacts. So we focused on 4 major energy transitions. Those are listed here. So we have renewable energy deployment, transportation electrification, fossil fuel retirement, and residential building decarbonization. And rather than proposing new metrics, the goal was really to synthesize what already exists in the literature and provide a more structured way to evaluate equity outcomes. And that leads me to our framework. So if you are familiar with the energy justice literature, you probably have seen a ton of different frameworks that are kind of within the scholarship. Our work builds on the foundational environmental justice and energy justice frameworks, which typically emphasize these 3 dimensions here on the left. So we have distributive justice, which is how benefits and burdens are distributed, procedural justice, which is who is able to participate in decision making, and recognition justice, so whose experiences and needs are recognized. I think these frameworks are incredibly important conceptually and theoretically, but they don't always really translate into tools that can be used to evaluate policies or programs, especially for practitioners or people outside of academia. So after our literature review and compiling over 100 metrics, we were really thinking, how can we move from this kind of theoretical framework towards something more operational and something that can actually be measured? So to address that, we developed an analytical framework that organizes energy equity into 3 dimensions, which are health, access, and livelihood. Health really captures the physical and mental health impacts, so things like pollution exposure or avoided health risks. Access focuses on the ability to obtain and benefit from different energy transition technologies and programs. And then livelihood captures economic well-being, so things like employment, income, and energy security. So this slide shows the base of our analytical framework. So like I mentioned, it organizes equity into those 3 key dimensions: health, livelihood, and access. And each of those dimensions includes a set of indicators. So for example, within health, we have 4 indicators. One of those is pollutant exposure, and another is different health outcomes. And these indicators were really developed based on the set of metrics that we identified throughout the literature. So we categorized those metrics and then developed these indicators. And each of them, the indicators, can be evaluated using a variety of different metrics, but those should really be adapted depending on the context. So whatever transition or specific energy program or policy that you're trying to evaluate, different metrics will arise. So really the goal here is to move from these broader concepts of equity into something that was more structured and measurable. And importantly, the framework's not meant to prescribe a fixed set of metrics, but more so to provide a way of organizing and comparing different types of equity impacts. So to make this a little bit more concrete, I'll walk through an example. So this is what the framework looks like with different metric examples for each of the indicators. So how can it actually be applied in practice? I unfortunately don't have time to go over all of the 4 different transitions that we covered, so I'll just focus on one example. So let's say there's a city that's considering designing a new incentive program for residential building electrification. So this might include incentives for installing heat pumps or electric appliances. And as part of that process, they really want to consider the full range of potential equity impacts that could arise, whether they're positive or negative. So under this health dimension, they might look at metrics like indoor air pollution from gas appliances. So that would be pollutant exposure or associated respiratory health outcomes. And under access, they could look at adoption rates of electric technologies or participation in the incentive program. So essentially who's able to benefit. And they could look at those by different demographics. So adoption rate by neighborhood, by race, or by income. And then under the livelihood dimension, they might evaluate metrics like energy burden, so which is the share of income spent on energy, and how that changes with participation in this kind of incentive program. So this framework hopefully can help guide decision makers to consider equity impacts across multiple dimensions rather than in isolation. But I think it's also important to consider that how these metrics are defined and used in practice will really impact the equity outcomes. So for example, a program could appear successful in terms of the total adoption rate, like maybe they have a high rate of adoption of heat pumps, but it could still fail to reach the households that are experiencing the highest energy burden. Okay, so building off that example, I just wanted to give a few key takeaways from this work and from what the framework can actually enable. So like I mentioned, rather than prescribing a single set of metrics, the goal was really to organize what already exists in the literature and bring together a diverse and fragmented set of metrics across disciplines and transitions. And in doing so, we hope that it can support more systematic evaluation of equity outcomes. It also allows us to consider impacts across multiple dimensions, so health, access, and livelihood, rather than focusing on just one. And importantly, it was really designed to be flexible and adapted to different contexts and not just applied uniformly. So while the framework can really help us organize and structure how we evaluate equity, it doesn't really resolve all of the underlying challenges with kind of metrics-based equity evaluations. So first, metric selection is inherently subjective. So different studies and different stakeholders might choose different indicators and different metrics to measure equity, which means that they end up highlighting different aspects of inequality. So second, data availability can really constrain what we can measure. So in many cases, the data we would need to fully evaluate equity simply doesn't exist. And third, some impacts are really difficult to quantify. So things like cultural loss, lived experience, and historical inequities. So for example, if an indigenous population is forced to move, so they're displaced due to like a dam construction, it's really hard to quantify the cultural loss that they have experienced from being removed from their ancestral homelands. So even though metrics are really essential for evaluating equity, they can only really capture part of the picture. And different measurement choices can ultimately lead to really different conclusions about who is most burdened or what the inequalities are. So metrics can't tell the full story of energy inequity, but they really can help provide policymakers and frontline communities and other stakeholders with some of the tools needed to create change. And the goal for this research is hopefully to make equity considerations more central in planning for the energy transition. The framework and metrics are intended to be used in all stages of decision-making processes, from program development through implementation and evaluation. And hopefully in the future, these types of energy justice and equity concepts will be widely accepted and implemented as we work towards a just transition. Thanks, everyone. I have my contact information here. You can feel free to reach out, and I'm happy to answer any questions.
Great. Thank you so much, Sage. And for those that are interested in looking deeper into these equity metrics and seeing the full slate of metrics that Sage developed with her research, we actually have a webpage on 2035 Initiative's website that kind of lays them all out in diagrams and has some of those cool wheels that she showed you during that presentation. So maybe Carrie, you can drop that link in the chat so the participants can see. But thank you, Sage. And with that, I will go ahead and invite up our final presenter of this panel. Sergio, take it away.
Right on. Thank you so much, and great presentations to my previous colleagues. Sergio Castellanos, UT Austin, and today I will be talking about residential PV in the US, mostly the seeding effects, but also the household financial impacts. This is work done and led by my students at Morteza Maleke, but in reality, it reflects the spirit of this lab, the Reset Lab, which is to bring students together from multiple backgrounds to use data science and engage with communities to support and address the energy transition in an equitable way. So we care deeply about technologies and how they impact society, and we work hard to mitigate the potential and from disparity that might arise from that adoption. And one of those technologies that we are very interested in is solar PV, which is the theme of today's conversation. So years ago, when solar PV was taking off, there were many questions on whether the deployment was actually fair, or if there were disparities that would cut across income. For those of you who have been, many of you, I would assume, immersed in the environmental justice field, you might know that race is a stronger proxy to identify whether an injustice takes place more than income. And so some years ago, there was an immediate question where these articles were coming out and asking whether US residential solar is just for the rich. And bringing that spirit from the environmental justice, one of the questions was if this persistence of inequalities could also be reflected or might emerge actually across racial and ethnic dimensions. And so that led to a work with my colleagues, Professors Deborah Sunter at Tufts University and Professor Nankaman Johns Hopkins. So we assessed the installation patterns across racial and ethnic groups. And so what you see here is a plot. On the x-axis is income, on the y-axis is the solar deployment. We compare this against a well-mixed census tract. And this is well-mixed. I mean, there's no majority of a racial ethnic group. And what we see is that as we bring installers that are white majority census tract, there is a over installation compared to the no majority. It's the baseline. But then when we bring minority groups, Hispanics, Blacks, they tend to underperform. Asian, it's a mix of both. And sometimes this under installation, which is critical to highlight that it's even if you control for income, that tends to be under installing. And so, and sometimes that was even up to or down to 70%, again, at a certain portions of the income spectrum. Now, importantly, this was a snapshot in time. And a question that was left unanswered back then was the aspect of temporality. And so an important dimension to understand this is adoption process is the peer effects. Now, the reason for this is that they can serve as networks, which are channels where through information tends to diffuse. And so information could be about the benefits, the cost, the logistics of PV adoption. And so that once information is passed along, that can reduce the uncertainty to adopt and therefore increase adoption rates. So this has been extensively studied, many researchers, great scientists, but never quite with a quantitative framework that also reflected this racial dimension previously explored in the other work. And so the research question here to analyze is, how does the seeding impact the diffusion of solar PV? And does it vary across different racial and ethnic groups? So to answer this question, we leveraged the data provided by Stanford through their Deep Solar Plus Plus project, which they acquired through very detailed satellite imagery that they capture over time. And so they train a convolutional neural network, and that can detect what is a rooftop versus what is a PV installation. And so this then is coupled with the census data from the ACS. From that, we create a conceptual framework that establishes first, if there's a region with multiple households within a census block group, there will be no installations at time equals 0, but then at an incremental step, you will start having more and more. And so throughout this, we can understand when the first seeds are planted, which is the treatment, but also how quickly or how strongly do they diffuse throughout the block group. So we also establish a threshold because sometimes there could be false positives of a solar PV installation. And so with that in mind, at each time step, you have a node that becomes activated if there's a weighted proportion of the neighbors surrounding that meets or exceeds that threshold. So in other words, we try to determine whether the peer influence is greater than or equal to the threshold that is considered as a seeding effect. So after we established this household network effect, we aggregated the blood group level. We use a parametric event study model where we have our outcome on the left-hand side, which is the solar PV uptake. On the right-hand side, we have fixed effects that capture the heterogeneity across regions and years. We have some control variables, as you can see, income, education, age, density. Our beta in this case is the parameter of interest, how strong that seeding effect is. And then we have our first seed indicator and unobserved confounders. Now, without further assumptions on the confounders, we can't estimate this parameter of interest. So we acknowledge pre-installation, we estimate a pre-trend, we extrapolate that function post-treatment, we detrend the outcome, and then we estimate the treatment on the detrended outcome. So what we see here is the result from that work. Basically, on the y-axis, we see the effect or the normalized PV uptake. On the x-axis, you see the pre and the post-treatment effect. And we see that there's a steep rise from years 1 through 4, but also that there's some wide confidence intervals, which points towards some heterogeneity. And so if we start teasing out then the seed impact and how does that propagate over time, and we do this on a racial ethnic lens, we can see that we begin first with the white majority block groups. We see that there's a gradual and consistent growth from years 1 through 5 on that uptake process. Now, Black majority communities, we bring them again the same graph. We see it's a higher initial seeding compared to white majority communities. However, their growth is lower over time and it starts to decrease. For Asian majority, we have a slower uptake initially, but then the adoption accelerates over time. Note that there's wider confidence intervals just because we have relatively lower numbers of blockers that are majority Asian. And then lastly, for Hispanic majority, we have a more pronounced increase in adoption over time. So the last piece is no majority, somewhat similar to a Hispanic majority census block group. So the takeaway by looking at this graph is that we have a Black majority communities, they have highest initial adoption, but their seeds impacts stabilize and decay over time, as you can see by the red colored dots. Hispanic majority groups, they are slower in their initial uptake, but they grow strongly over time. So it's a slow diffusion, but it's sustained. And this, in essence, from this graph, we can conclude that not all seedings and not all diffusions are equal. So that said, once you install PV, you might think that everything is good, right? So our next logical question was, what are the household financial well-being implications? So, you install it, what does it mean to your pocket? Now, this question was a logical question, the follow-up to this first analysis, but it's also fueled in part by reports of predatory loans and a lack of ground truth data, meaning sometimes these estimates of benefits are either simulated through cash flow analysis or survey-based, but in very small populations, and just looking at the perceived benefits. So what follows is a work in progress with colleagues from LBNL, Eric O'Shaughnessy and Galen Barbos. But this is the question that we are set to answer, the household financial well-being impacts of solar once it's installed. And one of the first things that we try to understand is how the consumer base has evolved over time. What you see here is data in terms of installations from LBNL's Tracking the Sun database. And then we couple that with Experian consumer credit data, which provides yearly individual level observations on a national U.S. representation from credit file holders from 2010 through 2023. This Experian credit data covers a wide range of outcomes. It can be household income, credit score, outstanding credit balances, available credit, mortgage information, debt to income ratio. But what we see here is that early cohorts, 2011 to 2015, as shown in blue, they are sharply concentrated on the x-axis credit score, on the y, it's a kernel density, so it's density. They're sharply concentrated at the high end of the credit score distribution, meaning in this region, that's light blue. They're typically around 750, the mass heavily concentration there. But then as cohorts evolved over time, we see that they start to shift towards the left-hand side with the cohorts from 2019 to 2023. They're shown in red. They start to exhibit a greater density in the 500 to 700 credit score. And that's also marked with a reduction in the high score peak. It's important to highlight that, provided a little bit of historical background to this, in early years, PV installations were mostly cash or also third-party ownership TPOs, either PPAs or lease. But then around 2017, well, 2015, but in 2017, there was a solar loans boom. That was the case that by 2020, they constituted for more than 60% of residential finance transactions. So just keep in mind that as we progress over the graphs. Now, this deepening and broadening of access can be also resolved across states. Here you see state-level temporal trends in the share of residential PV adopters by credit score. So low credit score is in the top, high credit score is in the bottom. It's inverse. But it's done for California, for Texas, New York, and Florida. We observed a pattern, which is that the share of adopters with a low credit score, in this case, the top row, it rises steadily across all markets, while the share with the very high credit scores, starts to decline markedly as well. Now, the y-axis tend to be indicating different levels of pace and penetration, and they might vary across states, but the directional pattern is quite consistent. Now, what's important to highlight is that it captures the progression and the reality that households with diverse financial characteristics are entering the market that is at its lower financial margin, but it's also some of these households could potentially have a more constrained capacity to absorb a new long-term debt obligation. And so this has implications because as we see, these households can be associated with detrimental financial well-being outcomes. So what you see is the outcome of an event study from a stacked diff and diff specification, where the y-axis reflects increase in delinquency, in this case reflected by the missing a 30-day period for credit payments, and on the x-axis is the event pre and post installation. So in here we observe that on average across the full spectrum or the full sample, solar PV adoption is associated with an increase in short-term delinquency post-adoption. So this suggests that there is a possible adverse financial impact of PV adoption on the broader adoption population. However, is this, the next logical question is this true across all adapters? And so what our preliminary results indicate is that there's a consistent and striking pattern, which is the delinquency of solar PV adoption is much higher and more precisely estimated among low credit score households, as you can see in the left-hand side, where the magnitude, which is shown on the y-axis for delinquency, is higher for the blue bars, which corresponds to low credit scores, than the orange bars, which is high credit scores. And this is true across all states that we evaluated earlier on. So the same goes for income, where low is in blue and high income is in orange, and the same magnitude and estimated precision is distinct across all segmentations. So this evidence points then to a need to better understand if the benefits are truly materializing for everyone once they install PV. Needless to say, this also opens the question to other technologies too, especially as we race to electrify our economy. We heard great conversations about a smart thermostat, or it could be about storage, or you name it. And this also, moves us to look for next hypothesized drivers for this. It's still future work or ongoing dash feature, which is looking at potential drivers such as like undisclosed dealer fees that increase the loan principals by 20-30% as it's been reported in some instances. It could be maybe a systematic overestimation of the savings that leaves the whoever's borrowing the money exposed to an anticipated net cost, or just an individual disconnect between what we think we're consuming versus what we're saving, and that leads to some potential rebound of sorts. Still TBD. So as key takeaways, for seeding impact, while Black majority have the highest initial adoption effect early on, its seed impact stabilizes over time. Hispanic majority, they have a strong, slower uptick, but then stroke division over time. And in terms of the financial well-being, access and benefit are not always equivalent. And I think it was in the previous conversation by Sage when she showed the framework for equity dimensions. That's an important piece because there was this access and then the livelihood. So in this case, one does not lead to the other one from what we're seeing, at least not in some segments of the population we analyze. And then lastly, which is one of the more important realization, is that this equity promise of PV depends on how those financial terms are arranged through which the access is extended in the first place. Thank you.
All right. Thank you so much, Sergio. I think so often in the climate and energy policy world, we think, we can just make solar cheap and it's just going to all roll downhill from there. Everyone's going to adopt and we're going to get this rooftop solar utopia. So I think research like this is really important to remind us that there are other barriers we have to consider, but also all other opportunities in that, in getting this and allowing it to benefit communities. So thank you so much to all our panelists. We are now going to move into a Q&A. So I have a few questions that I'm going to ask some specific panelists and also the three of you at once. But for all our other participants out there, please type questions into the Q&A box. And after I ask a few of mine, we'll get to all of your questions. So please pepper questions into that little Q&A thing at the bottom of your screen. My first question is for Michelle. I think one thing that really stood out to me when I was reading your paper that you just presented on is this finding that about 1 in 10 households have been found to keep their home at an unsafe temperature to reduce energy costs. And that was just like blew my mind. Like 1 in 10 folks are at an unsafe temperature just to lower their bills. And we know we're living in a regime of skyrocketing energy bills across the country and especially in California. So if I'm a policymaker and I see that finding, I'm like, alarm bells are going off. So I'm curious, like, what do you think, if you are a policymaker that is shocked by that finding, that you could do in the near term to help address that thermal equity problem?
Thank you so much. And it was so great to hear everyone else's amazing research related to this topic. It's oftentimes hard to keep up with everything that's being published. So forums like this are awesome. So thank you so much for having me again. Yeah, it's, I think, a really great question. I think jurisdiction matters in this scenario as it does with a lot of policy making. But if we're keeping it like broad strokes in general, what do I think policymakers should be focused on and paying attention to as it relates to trying to improve thermal equity, especially across race and income? I think a multi-pronged approach, like often things are, would be required. A lot of the focus of my other research focuses on energy assistance. So I am very deeply inclined to note that a lot of the assistance that people can gain access to in order to afford their energy bills is like pretty historically underfunded, in which a lot of times the demand for it is not really met by the amount of funding available for things like the Low-Income Home Energy Assistance Program. I think we could increase funding so that we could directly help people afford their energy bills through public assistance is a really important component. Advertising it, doing targeted outreach in these specific communities would be really valuable. Another aspect would be to consider, have states consider improving and engaging more deeply in strengthening their disconnection protections. So most often states have protections in place whereby they cannot disconnect communities or individuals at a specific time of year. Most states have these for the cold, but a lot of states do not have these for the hot. So as extreme temperatures start to, I don't have to explain in this group, but as extreme temperatures start to expand in the United States, there is really a policy disconnection between the disconnection protections that are in place and what's actually going to be required as people are going to have harder and harder times in the extreme heat. So I think federal level, really thinking about modernizing and expanding assistance. That can be direct bill pay, weatherization efforts, improving efficiency at the household level through weatherization assistance. At the state level, disconnection protections. And then, of course, there's always targeted interventions that utilities could do. I think one piece of research and one avenue that isn't actually talked about enough is to think about like a baseline level of energy that a household, an average household requires in order to keep their home at a comfortable temperature and refrigerate their food. What is that baseline level? And if you need a disconnection, maybe we shouldn't be disconnecting people. What we should be doing is saying you can only use this amount if you're in arrears or if you've missed a bill. Like the most humane way to really think about this is to think about like what is that baseline level for a low income household, for a medium income household, for a high income household, and maybe like let's hit that, right? Let's keep people safe in their homes. And then if they can't pay their bill, then they can't charge their electronic device. They can't turn on their TV. They can't connect to family and friends. All negative social outcomes, right? But we can keep them safe in their homes. So I think that's like a utility level fix that requires some evidence-based work that I think should be done at utility levels. And I think would require some a grouping of federal and state regulators to think through how that would go. So those are some like three at three different jurisdictions, some impacts or policy fixes you could consider, depending on what type of policymaker you are.
That's really great. Well, like I said, I hope that policymakers are paying attention to your research because I think that's a really important finding. Um, my next question is for Sage. And I think one thing that came to mind when you were presenting your framework is that there are times when, one of these metrics, one dimension improves and another degrades, right? So you kind of have this trade-off of like one gets better, but the other gets worse. So, for example, maybe a gas plant retirement is going to produce health benefits for the local community, but there's going to be job losses for that community as well. So when you were putting together these frameworks, how did you think about like how someone should weigh these frameworks against each other, especially when making a policy decision?
I think that's a really, really great question and an important point for me to clarify like the purpose of the framework. So it's not really a decision-making framework, so it won't help like a practitioner know exactly how to weigh these trade-offs. It's more so meant to help them make the trade-offs visible. So whereas maybe they were only considering something like job loss, now they can also look at the health benefits as well associated with like a power plant retirement. So really it's hopefully intended to help equity impacts be more visible. But in terms of trade-offs, I mean, that is a practical question. And I think people might prefer different approaches to doing that, to weighing kind of these metrics or impacts against one another. So, for example, like some might want to monetize each of the metrics, especially like economists maybe see the value in like converting everything into dollars so that they can easily compare one to one. I think for equity outcomes and in the environmental justice field, that monetization can be like a little bit problematic, and there's been pushback against that. So I think instead of just asking whether health benefits outweigh livelihood losses, there's a more productive approach to using this type of equity evaluation framework or any type of kind of equity evaluation early on in the planning process. So, for example, let's say the planners in this case are looking at this gas or oil power plant closure. And if they're looking at that early on, they can kind of anticipate what the potential impacts are going to be and then design policies that address those. So pairing this power plant closure with workforce supports for the displaced refinery workers, and wage replacement and job training. So that's kind of addressing those negative livelihood impacts while still benefiting from the health ones. So I think it's less about like weighing between them and more about addressing them together with better planning.
That's great. Yeah, thank you for the clarification and the answer. And I agree that this is definitely a useful tool for sort of identifying the problem space and trying to, I mean, just even looking through the indicators on our website, have new language and new frameworks to think about different dimensions of policy decisions, even if it isn't a decision framework. So that's great. Um, my next question is for Sergio. So your findings seem to suggest that the absence of having someone who has rooftop PV in a community is itself a structural barrier to deployment, what you found with these seeding effects. And if that's the case, then it would seem to suggest that your standard just income-based incentives, make things cheaper for folks who are lower income might not work as well in those unseeded communities. So what does our policy toolkit look like for those unseeded communities? Like, how do you have to think about the deployment policy different in those places?
Yeah. So I think it's a two-step dynamic approach that addresses different cadences. The interesting thing about this is that we could track things over time so we can see the immediate effect, the acute, and then the chronic, if you will. So we can also see the supply and demand side support. So from the supply side, I think we still need that push to continue installing, that fostering of adoption, maybe provide or continue providing solutions to lower that upfront cost. But of course, the second part of the talk talks about some of the issues in doing that or potential roadblocks. But I know, for example, that there are organizations that they spurred a program just to look for those locations that don't have installed, but installing places that have great visibility. And so they were working with places of faith-based locations, like churches and whatnot. And the idea there is like, well, this has a big visibility. Why don't we install there? And then the whole community that approaches this location, then we'll get to know more about the installation. So I think that supply side, I think it's important, and sometimes it requires creativity, but also being intentional. That might sometimes go against business models that try to lower acquisition customer expenses. And so there's a friction potentially in there. But the other side, I think, is the demand side support. And as Professor Graf was showing at the end, advocating for educational initiatives, I think something like that is also pretty much needed in this space, is long-term trust building efforts, community outreach, demystifying some of the challenges, but also clarifying potential risks. In other spaces, when we think about and speak about resilience, an important piece is this culturally relevant engagement. The messages that you put across, sometimes they're not conveyed properly if it's not in that specific context. So that encompassing educational programs, it's another piece that it's, I think, sometimes underestimated and much needed to sustain that growth over time. Otherwise, it might decay, as we saw.
Yeah, absolutely. Okay, I have a few questions that I'm just going to ask the panel generally, and anyone can just jump in and answer. And the first, I think, zooming out a little bit, all of your research talks about, in some way, about some equity gap, right? Some where communities are facing disproportionate burdens. And I think sometimes in the climate conversation, like closing those gaps and decarbonizing are talked about separately. Like these are two separate things we have to do. We have to decarbonize and we have to address these equity concerns. But I don't think that's quite right. And I think your research shows how this can not only be equity, these equity concerns can not only be central to decarbonizing, but it can actually accelerate decarbonization and actually be what a tool we can use to cut pollution faster. So I'd love to hear from you all based on your research. Like, how can alleviating energy burden and energy insecurity actually accelerate the clean energy transition? Anyone can jump in.
I'll start. I'll just say, I think people understand messages in different ways, and sometimes the decarbonization piece might not resonate that much. But when you talk about savings, that could be an important driver. We've seen now with our technologies, as we're thinking for example, induction cooking stoves. Maybe for them, it doesn't matter too much what type of stove, but if you tell them like there's a high propensity for their kids to develop asthma if they're exposed to natural gas long term, then that might incite them to actually push for that decarbonization angle without even having anything to do with decarbonization to begin with. So I think there's many angles, and going back to SAGE framework, I think if you look at the health implications, the livelihood, the access, everything centers on decarbonization, but it's through different tangible manners in which people can relate to. And so I think, if anything, we should go back to that framework and look at those opportunities that, hey, what in this roulette we can pick to have a conversation that can help us push decarbonization further.
Yeah, I'll just jump in. I don't think we can reach our goals, like our decarbonization goals, if we ignore low middle income communities and or more like historically marginalized communities. I just like they make up too big of a part of our population, and they're too important a part of our population to ignore the fact that if we are going to, right, the decarbonization effort, again, is going to have so many prongs, right? We need to do it through solar panels. We need to do it through electric vehicles. We need to do it through residential upgrades. And if we're sort of not able to consider the needs of the lower income and or historically marginalized communities in this transition, then they will not transition, right? There is a lot of really great work on this related to the impact of leaving residences like lower income and historically marginalized communities connected to poor infrastructure, and not upgrading them to more electric options or electrified options. And the impact can be like really devastating, leaving them in an even worse position and making it later even harder to decarbonize them because they're less likely to be able to access those upgraded types of infrastructure, right? So like really addressing these infrastructure gaps across all sects of our community is really like the only way we're actually going to meet decarbonization goals. So like if we think about trying to cut costs, right, related to efficiency in residences or electric vehicles or energy bills, that hopefully frees up some opportunity for these households not only to think about like electrification, but also like being able to pay their grocery bill and being able to drive, buy gas so they can drive to a home, which frees them up to even notice the fact that an electric vehicle charging station is nearby, and maybe they should consider buying an electric vehicle. What would that do to their bill, right? So I really genuinely think like there's no energy transition without considering that just part, like just an equitable energy transition. An energy transition requires like a certain proportion of the market to actually shift, and we need that proportion of the market to shift, and that's going to include, I think, low and middle income and historically marginalized communities as well. So thinking about them separately, I do not think does a service to the end goals. Does that answer your question? I just don't think you can really separate them to meet the goal.
Yeah, absolutely. Um, That's great. And you mentioned electricity rates, and this is on the tip of everybody's tongue right now. In California, in the climate policy world, in the energy world, rates are going up, and especially here in California, they are going up fast. And it's harder to make an economic case for electrification when, if someone trades their gas furnace for a heat pump, they might not actually save money. Yeah, that machine is a lot more expensive, but when electricity rates are 5 times, 6 times, 7 times the price of gas, you aren't actually saving money. So I'm curious, like in the years that you all have been doing this research and watching these electricity rates go like this, like how how can we continue to make progress when rates keep going up? And like how can we protect these low income residents who maybe they did adopt a heat pump last year, but now they're seeing their rates go up and it is becoming a financial burden, like some of the burdens that Sergio, you mentioned in your presentation. Anyone can jump in. What do we do about these rates?
I can go because I'm not embarrassed to say my answer is a bit of a question, like, what is going on? Like it's so like affordability obviously is this like politically quite fragile question, right? But it's one that's been really at the core of questions of affordability have been really at the core of what I've been thinking about and working on quite deeply. And I think like I do not have an answer. Like, how do we move forward? I think as researchers, the thing that we, or at least I feel like I have to do right now, is try to collect as much evidence as I can to better understand how all of the changes to our grid and all of the changes to our energy demand that are currently coming our way are basically going to impact the grid, and ultimately what can we do to shore up the durability of our grid in a way that is equitable, right? And in a way that is just. And I think a big area that remains a little bit of a black box that I'm hoping to continue to sort of like better understand is our state energy leaders, right? Like what's going on at the public utility commissions. What are the pressure points? What are the implementation points in those spaces for us to have a better understanding of how we can ensure that just and reasonable rates are actually being adjudicated in those spaces. And I think there's real value in each of us like collecting evidence in our spaces to like have a collective understanding of what's going on with relation to electricity rates, because there's so many different actors, right? There's so many different actors, especially out east with PJM, and like there's so many different actors to understand. And I think our best bet is sort of tackling it bit by bit and trying to understand the stakeholder connection altogether. Yeah, it's such a wicked problem that I think we just have to follow really closely.
Jump in with this one too. I agree that it is such a wicked problem, and I can't help but be frustrated as to like, does it need to be this way? Like, do millionaires need to profit off of basic needs? Like, do we have to have investor-owned utilities? There are places where all utilities are public. Like I haven't done the research to look at the impacts between the two, but I almost feel like a complete restructuring is needed for how rates are actually charged. One of the metrics, I know someone also asked a comment about like energy burden metrics. One of the ones that I have from the paper I just pulled up, it was looking at like average annual utility rate increases in dollars per year. And in California, this is from Borenstein et al. 2021. Researchers estimated that solar incentive policies led to an average rate increase of 3 to 5 cents per kilowatt hour, which translate into an annual household bill increase of $120 to $230 a year. So because of the solar incentive policies that we had in California, low-income households ended up paying $120 to $230 more a year for their energy. And we know that they were the least likely to benefit from rooftop solar as well. So I think these types of problems, they're systemic and they maybe require like more than just advocacy, but maybe a complete restructuring of the system.
Yeah, yeah. And these conversations are happening in so many different corners right now in the energy space and the climate space and the equity worlds. It is the thing that everyone's thinking about and it kind of ripples through the whole system. But
And I'll
yeah, oh,
I was
sorry, go
gonna,
ahead.
yeah, I was just gonna say quickly because it's interesting. By the same token, I had my neighbor telling me like, "Oh, I wish I also had an electric vehicle just like you," because gas prices are, super high right now. And so then I look at the natural gas; they're quite cheap. So, maybe one sector is benefiting from electrifying, the other one is hurting right now. But I think that just calls to the volatility sometimes that you can experience with, some of the fossil-based technologies or just the fuels themselves. And they can be reflected at the consumer level, but also, we saw winter storm here in Texas in 2021. A lot of them that they were counting, load serving entities that were counting on natural gas because of the extreme weather event. They didn't have the means to supply. They were not hedged financially, so they went broke. And so I think there are financial repercussions also, not only for the end consumers, but also for companies in this approach of not diversifying. So if anything, in my mind, it just calls for having other means of reliable resources, which used to be the common knowledge or the common wisdom that fossils would be that reliable. We saw that that's not the case. And so that can lead to higher cost sometimes. And so it's a little bit of both worlds.
Yeah, absolutely. Absolutely. Okay, I'm going to turn to some Q&A from participants now. So again, just a reminder, if you have other questions, maybe some that have come up during this discussion, go ahead and put them in. We'll probably have time to get them to them. There's only a few in there right now. This first one is for Professor Graff, and this attendee would love to hear thoughts on LIHEAP distribution in Georgia, which I believe is the low income home. Oh no, you know the acronym. What's the acronym?
Yeah, low income home energy assistance program. You were totally right. You had it.
I was close. I was getting.
Yeah, you were getting there. Yeah. So, gosh, I'd love a follow-up. Like, what do you mean? So the way that LIHEAP works is that it's a federal program, and this is also very similar to weatherization assistance. It's just housed in the Department of Energy, whereas LIHEAP is in the Department of Health and Human Services. So they're housed in different places, which is a implementation question that we could chat about all day. But LIHEAP basically is an affordability federal assistance program aimed at helping people afford their energy bills. The way that it works is that the federal government appropriates money to states to ultimately administer their program. The program is ultimately administered by either local governments or community action agencies across the state. So there's a tremendous amount of federalism like question here. There's a lot of within state and state level variation. So the way, for example, that Georgia administers their program might be different than the way that Florida or Alabama, neighboring states, administer their program. An important component of LIHEAP is that some states only have heating programs, so help consumers in the winter. Georgia has both heating and cooling. Most states in the South have both heating and cooling programs. There's typically a weather divide there. And so the way that LIHEAP is distributed is often initiated by a customer, or a consumer. They have to apply, provide documentation of income eligibility, proof of residence, and of course, things related to their utility bill. Again, all of this is really state dependent, and these different implementation levers, outreach efforts. I actually have written a couple of papers about that and the impacts of those. But for the large part, main takeaways is that the more a state can streamline their application efforts and outreach efforts, participation in the program grows, and you have to spend less on overhead and actual implementation. So there's an efficiency gain there. And if this attendee has very specific questions about Georgia, please feel free to email me and I could talk about LIHEAP all day. So that's largely the scope of that program because it has a block grant nature to it. And the variation does allow for a tremendous amount of exploration as to what type of implementation might help improve program metrics. So yeah. I'll just stop there.
Great. We have another follow-up about LIHEAP, so I'm just going to ask this one now, which is coming from someone in New Hampshire, where we've been seeing months-long distribution delays, lots of uncertainty. I'm curious how communication networks in Georgia have faded, given LIHEAP algorithm revamp and federal LIHEAP staff cuts.
Yeah, so the impact on LIHEAP, the LIHEAP staff cuts, was it February, March, somewhere around then? They just to give a little bit of background to attendees who don't know, in February or March of last year, they cut the whole LIHEAP program from HHS. I think it was something between 14 to 20 employees at the federal level, which has basically created a bit of a bottleneck in terms of the funds going from the federal government being transitioned to state administration. And basically the state administrators, I think, have been doing all they can to try to beg the federal level to administer the funds or disperse the funds as quickly as possible. As far as communication goes, I think that outreach efforts and communication efforts about LIHEAP to specific targeted income eligible, historically marginalized communities has often been pretty weak. One of the reasons for that is that LIHEAP, as compared to something like SNAP, which is funded at about $60 to $80 billion a year, LIHEAP only gets $3 to $5 billion a year. And I think there needs to be real decisions about how much of that money is spent on assistance versus outreach efforts. So communication, I think, goes by the wayside anytime there is any kind of hiccup, even more so than it otherwise would be. So as far as how these determinations are playing out across the states, I'm assuming it's going to be a pretty similar pattern, comparing New Hampshire to Georgia, to wrap that up. So I would expect them to be fairly similar in terms of the challenges that they are facing, and probably pretty similar in terms of the trade-offs that they are making to try to keep the wheels on the train, basically. As of now, I do not have any ongoing work to study a pre-post given the LIHEAP reduction at the federal level, because I'm not exactly sure how to do that without qualitative assessment, and I'm not sure how to do that with state administrators being willing to talk to me about it. So if anyone has follow-up questions and thinks they have people who would be willing to talk to me about it, I would be very happy under this administration. I'm wondering under a different administration if conversations could be had more freely.
Yeah, great. Thank you. The next question here is for Sage, and this person would like to know, what is your viewpoint on the fourth suggested pillar, restorative equity? Where is the scholarship divided on it?
I think that's a really great question. For me personally, the idea of like restorative justice is critical because it's bringing attention to recognizing and repairing past harms. In terms of the energy transition, I think we could see like this being really essential when we're thinking about something like power plant retirements. So for example, as oil refineries shut down in California, how are those sites being remediated? So Phillips 66 in Los Angeles recently started closing down. That has been a site of pollution for the local community for decades and decades. And now they're wondering like what's going to happen to that site. Is there still going to be like leftover pollution, groundwater pollution, soil pollution, or is it going to be addressed by the responsible parties? And I think that's something that restorative justice gets at. In terms of the scholarship, I think it's a little bit less studied and potentially a little bit more difficult to evaluate and to assign responsibility legally. So the field's a little bit divided. But I'd say some like critical environmental justice scholars would argue that it's like essential. Otherwise, it's not really going to be a true just transition or real environmental justice without implementing all of those different dimensions.
Yeah, that's great. Thank you. Next question. I think this is probably for Sergio. Does the literature on DER equity indicate that compared to a myopic model, long-term foresight models would highlight what Lucas mentioned earlier, relieving energy burden as a long-term economic driver that actually minimizes cost for the whole system? And does it do that in any unique way?
I'm not even sure I understood the question, to be honest. Just like long-term foresight models, like capacity expansion, I would think. Uh,
I think that's what this question is getting at. Maybe they can chime in if they have a clarification, but you can answer that.
yeah. Well, relieving energy burden can actually minimize cost for the whole system. I think I'm trying to think in modeling terms. Uh, you know, energy burden would typically reflect households as a load profile aggregated at a given level. Um, and you install, I mean, you can reflect the installation of distributed technologies at a given cost. So I don't know, I mean, depending on how you model some of the cost, maybe there's a way to reflect the household impact on energy burden. And I'm coming from a place where, I question which households are benefiting, which ones are not. So I think it's very difficult to look at a household and say everyone will, will be benefiting without any secondary financial impacts. And so how to address that, put it in a model that it's macro, and then bring it out to the capacity expansion. That's an interesting question. I'm not sure. I need to think a little bit more how to parameterize that. But I think it's an important question on the basis of how do we reflect collective conditions into models, and I think that's a good question that the macro energy systems community has. We're typically thinking, how do we do this? I guess recently there's been some efforts to use RESTalk. So you look at statistical representative buildings and say, okay, at least that's what we've done some of the studies. Like, okay, if there's an adoption of this technology, what does it mean for their finances? And when you aggregate, you can say, oh, 65% of this city, giving the statistical representation of built environment characteristics, And if you model the consumption difference, let's say air source heat pump, then you can decrease the energy consumption for them, or the net savings are positive. So I think there is a way to reflect that, because then you modify that into a curve and then you look like a long-term plan. So I go back to my first portion of the answer. There's a way, but of course, I'll just say that there's always the need for that human validation, I think, to see if that's making the intended consequence. But yeah, that's one way in which I think things are being done.
That's great. Thank you, Sergio. And this is our last question in the Q&A. We have a few minutes for more if other folks have, other attendees have questions. But how does the emerging concept of energy community, so prosumers technologies, local energy trading to neighbors, how could that help alleviate issues of energy equity? If anyone has thoughts on that.
I guess my first reaction is, if you look at the tenets, if you're sharing the benefits and it leads to reduced cost, then that's good. If you had improved air quality, that's another distributed benefit that you're sharing against, with the community. If people took a role in the decision process, that's the procedural side of things, so that it's fostering energy equity. So I think, yeah, achieving energy equity can be reflected in many ways, and it depends on how that energy community is assembled and how they set their standards to operate, if you will. That would really define if equity is manifested or not. So I'm not sure the community per se by itself is the the piece, but how it's coming together rather. Hopefully that makes sense.
Yeah, absolutely.
One thing we could do that I've seen talked about a bit is that things like community solar or shared ownership can, in the way that they structure it, it's dependent, like Sergio was saying. But depending on the way they structure it, I do believe that there are regulations that allow for like tenants and low-income communities to become a part of the community, and then they are able to share in the benefits in a way that might have lower upfront costs than something like solar PV or rooftop solar on their individual home. So of course the catch is that like if these just favor wealthier tech-enabled homeowners, then of course that would not really solve any equity concerns. But if there are real pushes to ensure that these types of models integrate and also push into lower income and historically marginalized communities, and the regulations are set up that way, then I think it can have extreme promise. Yeah.
Great. Okay, I have one question, a speed round question for all of you to wrap this up. And that is based on all of the excellent and important research that you all have done on these energy equity and energy burden issues. If you had 10 seconds with a policymaker or a utility executive or some decision maker that could, have some influence over, pull some levers to make things better. What is the 1 to 2 sentence takeaway you want them to leave the room with? And anyone can jump in. It's the hardest.
Light needs to be funded at $40 billion a year to meet demand.
Love it.
I like that, straight into the point. I think I would tell them that if you're not explicitly thinking about equity outcomes and evaluating how costs and benefits are being distributed in whatever program that you're doing, your program or policy is already making equity decisions. You're just not seeing them, and they're probably negative ones.
Fantastic.
And I'll say maybe commit to looking at the energy transition not only from an intervention and that's it, but rather, follow through the process to really assess the benefits.
Great. That was great. That was very succinct. I thought that was going to be a lot harder question, but you guys nailed it. Well, thank you so much. We are just a minute from time, and I want to let people go on time, but really appreciate all three of you coming on today and sharing your research, sharing your wisdom with this community of researchers, of policymakers, we have students on the webinar who are just learning about these issues. So I think this has been a really valuable use of time to really dig into the nitty-gritty of like, what does energy equity look like? What does energy burden look like? And how can we actually take meaningful steps to alleviate those burdens? Um, I will say this is the end of our sessions today, but we are only half done with our energy justice workshop more broadly. Tomorrow we'll be back here at 9 a.m. Same link. We have two more panels. One, electrification for whom, equity in California's residential energy transition, and the other, again, more electricity rates, designing rates and distributed energy for climate resilience. So really zooming in even further on the household level in California with another great lineup of panelists and moderators. So thank you all, and hope to see many of you all tomorrow.
Thank you so much.
Thank
Thank
you.
you.
Thank you. Cheers.